Next, one more interesting feature about the crystalline solids, free space. What is meant by free space? Look, one thing is certain. However compact the system is, the particles are considered in the form of spheres. When these spheres are compactly arranged and systematically arranged, there has to be some empty space. There has to be some empty space. It has to be allowed. And this empty space is called as the void, or it is called as the interstitial space, and every crystal experiences such empty spaces. And the empty spaces are calculated with the help of packing efficiency. And in the theory part, you have familiar with, or you have calculated this and are familiar with such values of packing efficiency. In the simple cubic unit cell, if the efficiency is to be seen, this efficiency is about 52.4%. That for the simple cubic unit cell. And for the body-centered cubic unit cell, it is 68%. And for the face-centered cubic unit cell, it is 74%. Therefore, it is the simple cubic unit cell, and it is the BCC unit cell, and it is FCC unit cell. In case of the simple cubic unit cell, we say the packing efficiency is least. Look, we are just surprised to note that only half of the space is used by the particles, only half, just about 52.4%. In other words, almost half is in the form of empty space. In case of the FCC, 74% is used, but indirectly it means to say that 1/4 of the entire space is empty. Yet, it is supposed to be the most efficient packing. Face-centered cubic unit cell has the most efficient packing, while simple cubic unit cell has the least efficiency. In between them, we have the BCC, about 68%. If we know these values, then no problem in going through this question. The free space in CCP. Here, one more point we have to note. CCP, cubic close packing, FCC, face-centered cubic unit cell, and HCP, hexagonal close packing. I repeat, face-centered cubic unit cell, hexagonal close packing, and cubic close packing. All the three have same kind of or same magnitude of the efficiency, and efficiency is 74%. Therefore, in the CCP structure, 74% is used and 26% is empty, while in the BCC, 68% is used and the empty space is 32%. Therefore, sequentially, CCP has the empty space of 26% and BCC has the empty space of 32%. Thereby, 26% for CCP and 32% for BCC is seen in the option C, and option C is correct, and the free space for these two are 26% and 32%. I hope the questions are fairly easy. They appear to be easy only when we make a right kind of approach and a certain amount of logical interpretation. In the examination, I suggest you one thing. Don't go for the sketch of these unit cells because it is sheer wastage of time. Keep it in mind that corner contribution 1/8, body centered contribution 1. Calculate mentally. So that becomes 2 particles. Similarly for FCC, face centered contribution half, from 6 faces it is 3 particles, from 8 corners it is 1 particle. Calculation will be within no time, it is 4 particles. That way we shall continue with some more questions. So friends, we have some more questions. The first of them is the number of tetrahedral voids in the sodium chloride unit cell. So what is meant by the void? As we already know, in the closed packing system, there will be always the empty spaces. And these empty spaces are considered as the voids. In the packed structure, we come across the 2 types of such voids. Number 1, tetrahedral void, and number 2, the octahedral void. How they are produced? Now look, supposing it is one layer of the spheres, when another layer is to be placed above the first, in order to build the 3-dimensional structure, it is necessary to place these layers one above another. The layers of the particles, the layers of the spheres are to be placed one above another. In that, the particles hold the triangular depressions, like the particle of the upper layer will be holding the triangular depression of the lower layer. And when this depression is occupied with the upper layer sphere, an empty space is created. And this empty space is called as tetrahedral void. Something appears this way. Now, we shall simplify this one as it is the one layer. From that one layer, I pick up these 3 particles, triangular particles of one layer. I pick up the 3 particles of the lower layer and 1 particle from the upper layer, and I place it here. It produces an empty space in between the 4 spheres, and this empty space is called as tetrahedral void. Now, the question appears, if this is the first layer and the second layer, orange first and black second, what would be the next layer? The next layer works out in this pattern. You can clearly see the black particle is creating 2 tetrahedral voids. I repeat, the black sphere is creating 2 tetrahedral voids, one with the orange spheres and another with the green spheres. So I conclude, one particle can produce 2 tetrahedral voids. About the NaCl, we know NaCl is carrying face-centered cubic unit cell. The face-centered cubic unit cell has 4 particles in it, and each particle carries 2 tetrahedral voids. So the calculation becomes very simple. 4 particles, 2 tetrahedral voids per particle, and the total number of tetrahedral voids will be 8. So therefore, option, it is as simple as we can hope for. It is option 4, it is D. Number of tetrahedral voids equal to 8. So this way, the tetrahedral voids can be calculated. And for an additional information, we have number of octahedral voids. It is equal to the number of particles. One particle, one octahedral void. One particle, two tetrahedral voids. That is how we come with the calculations.